We will start in a couple of minutes. I will just share the slides. Is the slides visible? Okay. Good evening all. Welcome to VK tutorials of the NPTEL course Pericyclic Reactions and Organic Photochemistry by Professor S. Shangaraman from IIT Madras. Myself Anisha Suresh, PMRF TF for this course from IIT Bombay. So in today's tutorial we will be discussing some problems based on organic photochemistry. So in VK tutorials sir have mainly discussed regarding the photochemistry of aromatic compounds and electron transfer reactions. So we will be discussing some few problems based on organic photochemistry in the VK tutorials, and tomorrow there will be a summary tutorial from 5 p.m. Okay, now coming to question number 1. Find the product of the following reaction and give the possible mechanism. So, seeing the starting material and the reaction condition, that is photochemical condition, we can come to know that this is a oxa-di-py-methane rearrangement. Okay. So this is an example of oxa-di-py-methane rearrangement. So what will be the mechanism for the following reaction? Upon photochemical irradiation, this carbonyl will get excited and form O radical and carbon radical. Then that carbon radical will react with this alkene, resulting in the formation of a cyclopropane and a primary radical here. Then what will happen? this carbonyl this O radical will react with the cyclopropane, resulting in the bond breakage and lead to formation of another primary radical, which will recombine with this primary radical, resulting in the formation of a cyclopropane. So we will see the mechanism in detail. So upon photochemical irradiation, it will be forming this O radical, carbon radical, and this will also be forming radical. So these two radicals, they will recombine in this fashion, resulting in the formation of a cyclopropane. Then once this carbonyl is forming again, either this A bond can break or the B bond can break. So once the A bond is breaking, here a radical will be forming, as you can see here, like this. Radical will be forming, and once it will recombine, it will result in the formation of this cyclopropane ketone. Okay, is it clear? Under photochemical irradiation, so this carbonyl will excite and lead to formation of O radical and carbon radical, and this alkene will also form two radical, like this. Okay, then these two radicals will recombine, resulting in the formation of a cyclopropane. Once a carbonyl is forming again, this bond will be breaking, resulting in the formation of this intermediate. Then these two primary radicals, upon recombining, it will result in the formation of a cyclopropane, and this will be the final product that will be forming after the oxa-di-py-methane rearrangement. Is the mechanism clear? If there are no further doubts, we can move to question number 2. Coming to question number 2, find the product of the following reaction and give the possible mechanism. So this is the starting material, and it is undergoing a photochemical reaction. So what will be the mechanism of the reaction, and what will be the final product that is formed in this reaction? So under photochemical condition, this carbonyl will excite, leading to formation of O radical and carbon radical. Then what will happen? We will see the mechanism. Okay, upon excitation, it will form oxygen radical and carbon radical. Then this carbon radical will react with this double bond, resulting in the formation of a cyclopropane and a secondary radical. Then what will happen? This will result in the formation of a tertiary radical, as you can see here, like this. Double bond O. Here there will be formation of a tertiary radical, like this. Then that will undergo recombination, leading to formation of a cyclopropane, like this. Hmm? So first, under a photochemical condition, this carbonyl will excite, leading to formation of O radical and carbon radical. Then the carbon radical will react with the adjacent alkene, resulting in the formation of a cyclopropane and a secondary radical. Now what will happen? Once the carbonyl is forming again, this bond will be breaking, leading to formation of the more stable tertiary radical, and that tertiary radical will recombine with the secondary radical, resulting in the formation of a cyclopropane and a six-membered cyclohexenone. Okay, any doubts? So this is also an example of oxa-di-py-methane rearrangement. Is it clear, the mechanism? Okay, if this is clear, we will move to question number 3. Now coming to question number 3, find the product of the following reaction and give the possible mechanism. So you can see this is a 1,3 diketone derivative in the enol form, and it is reacting with this alpha beta unsaturated ester under photochemical condition. So what is the product that is forming here? Okay, so this is an example of De Mayo reaction where a 2 plus 2 photocycloaddition plus a retroaldol reaction will be taking place, resulting in the formation of a 1,5 diketone. Okay, so what will be the major product that is forming and what will be the minor product that is forming after this 2 plus 2 cycloaddition and retroaldol reaction, that we will be seeing in the mechanism shortly. So you can try it, you can work it out for 1 minute. Okay, now let us see the mechanism. So for that we should consider the electronics of these two systems. So when we will be considering the electronics, this sender will be electron deficient as the system is in conjugation, and this will be electron rich sender compared to this. And when we will be consider this alpha beta unsaturated ester, this will be the electron deficient sender, and this will be comparatively electron rich compared to this sender. So this delta negative delta positive will recombine, and delta positive delta negative will recombine. So the cycloaddition will be taking place in this fashion. So we will be getting this as a major product here. So now if we see, this is a beta hydroxy uh, ketone. So this is a beta hydroxy ketone which is an aldol product. Now it will undergo a retroaldol reaction, as you can see here. This bond will fall here, this bond will be breaking, leading to formation of an enol, as you can see. Okay, so this bond will be breaking. So this ring will be the six member ring will be breaking, and it will be converting into a 1, 2, 3, 4, 5, 6, 7, 8 membered ring, as you can see here. Okay, so so here this is 5, 6, 7, 8, 1, 2, 3, 4. Okay, so a double bond will be formed between 1 and 8, and a ketone will be there at 5 carbon, and ester will be at 6 carbon. So this is the product that will be forming after retroaldol. Now this is an enol. It can undergo ketoenol tautomerism, ketoenol tautomerism, leading to formation of this ketone. So this is a 1,5 diketone. Okay, So this is an example of de Mayo reaction. First, a 2 plus 2 cycloaddition reaction will be taking place, followed by a retroaldol reaction leading to formation of a 1,5-diketone. Okay, here head to tail alignment gives a major product because the electronics will be in such a way that it is favoring this reaction to take place. Now there is chance for head to head alignment as well, which will be giving the minor product. So if such a reaction is taking place, so here we are not considering the electronics. 2 plus 2 cycloaddition will be taking place in this fashion, leading to formation of this as the intermediate. So this is a beta hydroxy ketone. It will undergo a retroaldol reaction in this fashion, leading to breaking of this bond, and this 6-membered ring will expand into an 8-membered ring. So this enol will undergo a keto-enol tautomerism, leading to formation of this 1,5 diketone. So this will be giving the minor regioisomer if the reaction is taking place in this fashion, but electronically the other reaction is favored and it will give the major product. Okay, any doubts? So here we have to keep in mind about de Mayo reaction. So in de Mayo reaction, 1,3 diketone will undergo 2 plus 2 cycloaddition with any alkene, followed by retroaldol reaction leading to formation of 1,5 diketone. Okay, so this is also an important reaction when we are considering 2 plus 2 cycloaddition reaction. Okay, now coming to question number 4. Write the structure of the product from the photochemical intramolecular cyclization. So under photochemical condition in the presence of a sensitizer, what will be happening here? So seeing the starting material and the condition, what sort of reaction is taking place here? So it is a oxa-di-π-methane rearrangement that will be taking place in this condition. Okay, so let us see the mechanism of this reaction. What will be happening under photochemical condition? This carbonyl will get excited, leading to formation of oxygen radical and the carbon radical. Then that carbon radical can react with this alkene, leading to formation of a cyclopropane and a carbon radical here. Next, what will happen that we will be seeing. So it is a system containing a beta gamma unsaturated moiety. Okay, alpha, beta, gamma. So a beta gamma unsaturated moiety, and it will undergo a oxa-di-π-methane rearrangement. So here, first what will be happening? So first under photochemical condition, O radical and this carbon radical will be forming. It will react with this alkene, leading to formation of a cyclopropane and a carbon radical in this fashion. Now what will happen? We can number it in this 1, 2, 3, 4, 5, 6, 7, 8. Now upon formation of the carbonyl, this 1,6 bond will be breaking, leading to formation of a radical at 6 position. So how it will be? 5, 4, 3, 2, 1, and a bond is there between carbon 1 and 5. Okay, and here this is 6, 7, 8. A radical is present at this position and this position. Now this we can redraw. Okay, how we can redraw it? This is a 1, 2, 3, 4, 5, 5-membered ring, right? So this can be redrawn in this fashion. 1, sorry, this is 1, 2, 3, 4, 5. Okay, and in between 3 there is 8, 7, 6, and 6 is connected to 5. Okay, 8. One second, I have drawn one extra carbon. So 3 is connected to 8, 8 is connected to 7, and 7 is connected to 6. 8, 7, 6. At 6th position there is one radical, and at 4th position there is one radical. Now 4 and 6 radicals will recombine, resulting in the formation of a 3-membered ring. So 1, 2, 3, 4, 5, 6, 7, 8. So you should follow the numbering so that it will be easier to understand. This when we will just rearrange, that will give the structure. Okay, so this is also an example of oxa-di-π-methane rearrangement. So first what is happening under photochemical condition, this carbonyl will excite, leading to formation of the oxygen radical and the carbon radical. Now this carbon radical, it can react with this alkene, leading to formation of a cyclopropane like this, and a carbon radical at 4th position. Now what will happen? When the carbonyl will be regenerating, this bond 1,6 bond will break, leading to formation of the carbonyl and a radical at 6th carbon. Now if we will redraw it, like it will be in this fashion. Now this can be redrawn into this. Okay, this structure and this structure, they are identical. This can be redrawn into this, and when this 4 and 6 will recombine, it will result in the formation of this one, which is identical to this final product. So this reaction is an example of oxa-di-π-methane rearrangement, which is important in organic photochemistry. Is it clear? Now, if there are no doubts on this question, we can move to question number 5. Here, this is the starting material under photochemical condition. What is taking place? So, seeing the starting material, which is a ONO starting material. So, and under photochemical condition, it will undergo a Barton reaction, which is a remote functionalization reaction under photochemical condition. Okay, now what will happen under photochemical condition? This ON bond will cleave, resulting in the formation of O radical and NO radical, right? Then what will happen? This O radical will abstract a proton from the gamma position alpha b sorry gamma delta position. Delta hydrogen abstraction will take place, resulting in the formation of a radical here. That radical will recombine with the NO radical, leading to formation of NO here, which can rearrange tautomerize to form an oxime, which upon hydrolysis will result in the formation of the carbonyl compound. Okay, now let us draw the mechanism for the reaction. So under photochemical condition, this ON bond will cleave homolytically, leading to formation of CH3 2 3 O radical and NO radical. Now what will happen? This O radical will abstract proton from the delta position, leading to formation of a radical here, OH. Here a radical will be forming, CH3 hydrogen. Okay, here a radical will be forming. Now that radical will recombine with the NO radical, leading to formation of OH, NO, H, CH3. Now this can tautomerize, leading to formation of NOH, CH3, that is the oxime, and this upon hydrolysis it will lead to formation of a ketone like this. Okay, now since this H nu condition is only given, so here the product will be OH, NO, H, CH3. This is the final product in this case. And if hydrolysis is possible, if hydrolysis condition is given, then it will lead to formation of this ketone. Okay, alpha, beta, gamma. Gamma hydroxy ketone will be the product that will be resulting. Any doubts? So this is an example of Barton reaction. So this is an important reaction. So first, this ON bond will be cleaving homolytically, leading to formation of oxygen radical and NO radical. Then the oxygen radical will abstract the proton from this alpha, beta, gamma, delta position, leading to formation of a uh, secondary radical here. That secondary radical will recombine with the NO, resulting in the formation of this compound, which will be the final product in this case. And If this reaction is further proceeding to hydrolysis, that time this NO can tautomerize to leading to formation of this oxime, and this oxime upon hydrolysis, it will result in the formation of this gamma hydroxy ketone. Okay, under H plus condition. So here the H plus condition is not given, so we can stop here. So this will be the final product. Is this clear? So if this question is clear, we can move to question number 6. Propose a mechanism for this Hoffman-Loeffler-Freytag reaction. So they have mentioned this is an example of Hoffman-Loeffler-Freytag reaction. So this was taught in week 7 modules. So we are having an amide, and under these three conditions that is given here, this is getting converted into a lactone. Amide is getting converted into a lactone. So what will be happening? Under I2 condition, this NH2 will react with I2, leading to halogenation on this nitrogen. Then upon H nu condition, that bond will homolytically cleave, leading to formation of nitrogen radical, which can abstract proton from alpha beta gamma position, leading to formation of uh, alpha beta gamma delta. This position leading to formation of a radical here, which will recombine with iodine, leading to formation of halo compound, that upon in the presence of the base can react, and it will lead to formation of the lactone. So we will see the detailed mechanism in the next slide. So what is happening? So under I2, this amide nitrogen, it can react with iodine, leading to formation of this iodo compound. Okay, now under photochemical condition, this will homolytically cleave, leading to formation of NH2 plus radical and iodine radical. So the NH2 plus radical, it can abstract proton from the alpha beta gamma position of this amide, leading to formation of a radical here, which can recombine with iodine, leading to formation of this compound. Then in the presence of hydroxy, this NH3 plus, so the extra proton will be abstracted by the OH, leading to removal of water. Now what will happen? This lone pair on nitrogen will fall here, and this oxygen double bond, CO double bond, will go and attack in an SN2 fashion, leading to removal of iodine, and this will be the compound that is resulted. Now in the presence of water, this will hydrolyze, and it will lead to formation of a double bond O. So this double bond NH2 will hydrolyze to double bond O, resulting in the formation of the lactone. So this is an example of Hoffman-Loeffler-Freytag reaction. Okay, I will explain once again. So what is happening here? This amide NH2 lone pairs will react with iodine, leading to formation of this compound NH2 plus I. So that under photochemical reaction, it will undergo a homolytic cleavage, leading to formation of NH2 plus radical and I radical. This NH2 plus radical can abstract this proton that is present at this alpha, beta, gamma with respect to amide, and this proton will be abstracted, leading to formation of the secondary radical and this NH3 plus. Okay, now what will happen? This radical can recombine with the iodine radical, leading to formation of this halo compound. Now this NH3 plus extra proton will be abstracted in the presence of the base, that is this NaOH. Now what will happen? This NH2 uh, lone pairs, it will fall here, and this carbonyl double bond will go and attack on this position, leading to removal of I minus in an SN2 fashion, and now it will lead to formation of the cyclic 5-membered species. Now this NH2 plus in the presence of water, it will undergo hydrolysis leading to formation of this double bond OH plus, where this ammonia will be leaving, that can abstract the proton, or OH minus can abstract the proton, leading to formation of the lactone. Is this clear? How the reaction is taking place? So this is also an example of Hoffman-Loeffler-Freytag reaction. Last week also we have discussed one or two problems based on Hoffman-Loeffler-Freytag reaction. I hope the mechanism is clear. If there are no further doubts, we can move to question number 7. So here a halonitrogen species is given. Okay, so this is also an example of HLF reaction, that is Hoffman-Loeffler-Freytag reaction. So in the presence of H3O plus, this nitrogen will get protonated, and that in the presence of H nu, thus NCl bond will be cleaving, which will undergo this Hoffman-Loeffler-Freytag reaction, resulting in the formation of pyridine or piperidine derivative. Now we will see the mechanism. MENCl. So in the presence of H3O plus, the nitrogen will get protonated, leading to formation of NClH plus. So this intermediate will be forming, that under H nu condition. So this nitrogen Cl bond will homolytically cleave, leading to formation of N plus dot. Now what will happen? This radical can abstract proton from alpha, beta, gamma, delta, this position. This methyl proton will be abstracted. So we can show the methyl like CH3, hydrogen. Okay. So this will be abstracting one of this proton, leading to formation of the radical here. CH2 dot NH3 dot NH3 plus. Okay, radical will be formed here. NH3 plus. Now what will happen? This CH2 can recombine with the Cl radical, leading to formation of CH2Cl plus, okay, this will be formed, and in the presence of NaOH, this OH minus will abstract this proton, neutralizing the positive charge on the nitrogen. NH2. Now this can attack on this chlorine in SN2 fashion, leading to removal of Cl minus. So 1, 2, 3, 4, 5. 5-membered ring will be forming. NH2 plus, that upon in the presence of NaOH, removal of water will be taking, this proton will be abstracted and OH will be leaving as water, leading to formation of this as the final species. Okay, so this is also an example of Hoffman-Loeffler-Freytag reaction. So first part will be happening under presence of an acid medium. Thus nitrogen will get protonated, leading to formation of this species, which upon photochemical irradiation, thus NCl bond will homolytically cleave, leading to formation of N plus dot and Cl dot, that is nitrogen cationic radical and chlorine radical. Then this cationic radical will abstract this proton present on this methyl group, that is at the alpha, beta, gamma, delta proton will be abstracted, leading to formation of the CH2 radical and this ammon tertiary third butyl ammonium, sorry, tertiary ammonium salt, NH3 plus. Now the CH2 radical will recombine with Cl radical, leading to formation of CH2Cl, and this NH3 plus is already present there. In the presence of NaOH, this NH3 plus is converted into amine NH2, and the lone pair on nitrogen will attack on this CH2 carbon in SN2 fashion, leading to removal of the Cl minus, and a 5-membered ring will be formed. So this NH2 plus is present. So this is a positively charged amine species. In the presence of the base, this proton will be abstracted, and it will result in the formation of this as the final product. Okay. So this is the final product that is formed in this reaction. So this is an example of Hoffman-Loeffler-Freytag reaction. Is there any doubt in the mechanism of this reaction? If there are no doubts, we can move to question number 8. Propose a mechanism for this reaction. The key intermediate is a ketene. The role of heat or light is to promote the loss of nitrogen gas. You don't need to factor that into your mechanism. Okay. So here This is the starting material, an alpha diazoketone that is getting converted into this ester from the 6-membered ring contracting into a 5-membered ring. So this is an example of Wolff rearrangement. Okay, Wolff rearrangement, and this reaction will proceed through a ketene intermediate. Now please try to work this reaction out and try to find out the mechanism for this reaction. Okay, now let us see the mechanism. So this alpha diazo compound, it can rearrange in this fashion. So it will be, it can be shown like this species. Okay, now this can easily undergo elimination of nitrogen. So either it can proceed through a concerted pathway like this negative charge will fall here and this bond will shift here leading to removal of the nitrogen, or like this N, triple bond N, negative. So this will remove leading to formation of a carbene sort of species which will undergo a rearrangement like this, resulting in the formation of the ketene intermediate. Okay, so this 6-membered ring is now contracting into a 5-membered ring. See, here the ketene is getting formed. Now what will happen? The methanol will add on to this carbonyl carbon leading to formation of this species which can undergo tautomerization resulting in the formation of ester. So this reaction is Wolff rearrangement. Okay. So first, this is the alpha diazoketone. Alpha diazoketone is getting converted into a ketene either through a concerted mechanism like this, or through formation of a carbene and then rearrangement resulting in the formation of the ketene. So first the diazoketone can be redrawn in this fashion. Then this negative charge will fall here. This 1,2 bond will be breaking and it will shift to 6 position leading to removal of the nitrogen and a ketene is resulted, and the methanol that is present in the reaction medium, it can add on to this carbonyl carbon leading to formation of this enol species which can undergo a keto-enol tautomerism resulting in the formation of the ester. Is the mechanism clear? So this Wolff rearrangement, it can either take place under photochemical condition or it can take place under thermal condition as well. Okay. Now coming to next question, that is question number 9. Propose a mechanism and the product for the following reaction. So here a cyclohexanone is given and it is reacted with this alpha diso um, ester. So what will be the final product that is forming? So this is also an example of Wolff rearrangement. Okay. How it is taking place? So here double bond, this can be redrawn in this fashion, N triple bond N plus. Okay, so this will be a anionic species. This can add on to this ketone. A nucleophilic addition can take place. Okay, so let us see how the reaction is taking place. So this is the species that we have seen. So this is our alpha diazo compound. It can rearrange in it can to, it can it can rearrange in this fashion. This negative charge will fall here and this double bond will lead to formation of a negative charge at the center. So this negative charge can add on to this ketone of the cyclohexanone, resulting in the formation of this species. Now what will happen? This O minus, once it is falling here, this bond will be breaking and it will shift to this position and this nitrogen will get removed, leading to formation of this final species. So exactly, it is not a Wolff rearrangement. It is not going through a ketene intermediate, but this is also a sort of rearrangement of rearrangement involving diazo compounds. Sorry for the disturbance. I cannot do anything with that. So what is happening? We are having this alpha diazo compound. It will rearrange in this fashion, leading to formation of anionic center here. This anion can attack on the carbonyl compound, resulting in the formation of this intermediate. Now, once the ketone is forming back, this bond will be, if we are numbering it, 1, 2, 3, 4, 5, 6. This 1 6 bond will be breaking and new bond will be formed between this carbon 6 and this center, and removal of nitrogen will be taking place. So this will expand into a 7-membered ring. The 6-membered ring will expand into a 7-membered ring, leading to the formation of this uh, 1 3 carbonyl species. Okay, is the mechanism clear? So we cannot exactly tell this is a Wolff rearrangement. Now, if the mechanism is clear, we can move to question number 10. Write down the mechanism of the following rearrangement on photolysis. So similar reaction we have seen while we were dealing with 3,3 sigmatropic rearrangement. That is, this was an example of Claisen rearrangement. So Claisen rearrangement was taking place under thermal condition. So here the rearrangement is taking place under photochemical condition. So this is an example of photo Claisen rearrangement. Please try to work out the mechanism for this photo Claisen rearrangement. I will give a minute for working it out. So okay, what is happening here? This is the starting material. Under photochemical condition, this carbon-oxygen bond will cleave in homolytic fashion, resulting in the formation of an allyl radical and a phenoxy radical. Okay. So under photochemical condition, this will lead to formation of a phenoxy radical and an alkyl radical. Then this phenoxy radical can rearrange in this fashion, leading to formation of this species. So here this is forming a solvent cage, then it can recombine, leading to formation of CH2 CH double bond CH2. Okay, then upon proton abstraction, here a radical will be formed and it will aromatize to the final product like this. Okay, or it can be like this as well. First this radical will be formed and it can rearrange, leading to the aromatization. Or in the solvent cage, these two can recombine, leading to formation of this CH2. And then under photochemical condition, O radical, carbon radical will be formed, and then proton abstraction will be taking place and rearomatization will be taking place, giving back the product. So this is how ortho shift is taking place. Now when how para shift is taking place, we are having a phenoxy radical like this. It can rearrange in this fashion, leading to formation of this intermediate. It can recombine with the CH2 CH double bond CH2, leading to here what they have drawn should be like this. Okay, or it should be like this: double bond of CH2. Now this again can undergo excitation leading to formation of oxygen radical and carbon radical. Then this oxygen radical can abstract this proton and rearomatization can take place, finally leading to the formation of this product. Is the mechanism clear? So this is an example of photo Claisen rearrangement. The thermal Claisen rearrangement, similar mechanism we have seen while discussing 3,3 sigmatropic rearrangements. Okay, you can look back into it. So this is how under photochemical condition the Claisen rearrangement is taking place. Similarly, photo Fry's rearrangement also can take place, which sir have discussed in the lectures. Okay. Now coming to question number 11. So this was a question from week 7 assignment. So what will be the product that is formed here? So under photochemical condition, what will be happening to this 5-membered cyclic ketone? So what sort of name reaction is this? So this is an example of Norrish type 1 reaction. So in this case, first an alpha fragmentation reaction will be taking place as the primary process. Okay, so how it will be? Here an alpha fragmentation will be taking place. So since this will be leading to formation of a secondary radical, the fragmentation at this position will be favored rather than at this position, where it will lead to formation of a primary radical which will be less stable. So it will lead to formation of, okay, then alpha beta gamma. Here the gamma hydrogen will be abstracted by the carbonyl radical, leading to formation of another radical which will recombine with this already present radical, leading to formation of the double bond. Hydrogen, okay, Me, Me. So these two can recombine, leading to formation of Me, Me. So this will be the final product that is formed in this reaction. It is undergoing a Norrish type 1 reaction. So here we should not mention the stereochemistry, okay? This will be the final product. Here they have mentioned an alpha cleavage and beta hydrogen abstraction. So the beta hydrogen abstraction they are telling with respect to here this counting alpha beta, okay? If we are counting from this center after the alpha cleavage, it will be alpha beta gamma, gamma hydrogen abstraction when we will be counting after the alpha cleavage. So here they have counted with before the alpha cleavage, and that is why this is beta hydrogen abstraction. Is it clear? So this is an example of Norrish type 1 reaction. So we have seen many examples of Norrish type 1 and type 2 reaction in the last week tutorials. So you can kindly go back and check into that if you are having further doubts. Okay. If this question is clear, let us go to question number 12. Provide a mechanistic rationalization for each of the following reaction. So this was the starting material. It is leading to formation of the cyclobutane compound and this alkene under photochemical condition. So seeing the starting material and the product, can you guess what sort of reaction is taking place here? Is it Norrish type 1 reaction or Norrish type 2 reaction? This is an example of Norrish type 1 reaction. Okay, so first alpha fragmentation reaction will be taking place, followed by a decarbonylation reaction where the CO will be removed, and it will lead to formation of two radicals at these positions, which can recombine leading to formation of the cyclobutane, or otherwise this radical can further react leading to breaking of this carbon-carbon bond, and it will result in the formation of this two molecules of this species. Okay, so this is also an example of Norrish type 1 reaction where the primary process is alpha fragmentation and the secondary process is decarbonylation. Decarbonylation followed by recombination or breaking of a carbon-carbon bond and then recombination leading to formation of this alkene. Okay, now let us see the mechanism. So here the alpha cleavage will be taking place leading to formation of this carbonyl radical and this ben, tertiary radical here. A decarbonylation reaction will take place at the center by homolytic cleavage leading to removal of the CO, carbon monoxide, and these two radicals it can either recombine leading to cyclization giving the cyclobutane ring, or here this bond can break in homolytic fashion as you can see here, leading to formation of this alkene species. Two molecules of this alkene species will be resulted by breaking of this carbon-carbon bond. If we number like this 1, 2, 3, 4, this 2, 3 bond will be homolytically cleaved and a new bond will be formed between carbon 1 and 2 and carbon 4 and 3, leading to formation of two molecules of this compound 2. Okay, so this is an example of Norrish type 1 reaction. So first an alpha cleavage is taking place leading to formation of this diradical that will undergo a decarbonylation reaction. Removal of carbon monoxide is taking place leading to formation of this diradical. So this diradical can undergo two pathways. It can either recombine leading to cyclization giving the cyclobutane product, or it can undergo a cleavage of this 2 3 carbon 2 carbon 3 bond, homolytic cleavage of this carbon 2 carbon 3 bond leading to formation of a new bond between carbon 1 and 2 and carbon 4 and 3, leading to formation of two molecules of this compound 2. Okay, this is how the reaction is taking place. So this is also an example of Norrish type 1 reaction. Is the mechanism clear? So if it is clear, now we can move to question number 13. Give the product of the following di-pi-methane rearrangement. So this is an example of di-pi-methane rearrangement. So here the di-pi is coming from this phenyl ring as well. Okay. So how this reaction is taking place? So under photochemical irradiation, a diradical will be formed here like this. pH, pH. This radical will react with this double bond, leading to formation of a cyclopropane and a radical here, losing the aromaticity of this compound. Now regaining the aromaticity will be the driving force for this reaction. So upon regaining the aromaticity, this bond will be breaking, leading to formation of the more stable radical, tertiary radical. pH, pH dot, Me dot, that will undergo recombination, leading to formation of the final product. CN, pH, pH, Me. So this will be the final product that is formed in the reaction. So you can see this is the final product. So once again we can discuss the mechanism. So this is an example of di-pi-methane rearrangement. Under photochemical excitation, a diradical will be formed. pH, pH. This alkene will result in the formation of the diradical upon excitation. So this radical will react with this double bond, leading to formation of a cyclopropane, and the aromaticity of the benzene ring will be lost. Okay. Now regaining the aromaticity of the ring will be the driving force for the reaction. So this upon regaining aromaticity, this bond will be breaking, as it will lead to formation of a tertiary radical. Okay. Now these two radicals, it can recombine, leading to formation of a new cyclopropane ring. So here Me will be there, and here pH will be there, and this is the new bond that is formed. New bond we can highlight in different color. Sorry. So this is the new bond that will be formed finally. Is the mechanism clear? This is an example of di-pi-methane rearrangement. Now coming to the next question, complete the following reaction. So a carbonyl and an alkene is given. So it will be undergoing a 2 plus 2 cycloaddition, and this reaction is particularly known as Paterno-Bucchi reaction, and it will result in the formation of oxytane skeletons. This reaction also I think we have seen in the last week tutorials, similar reaction. So what will be happening here? Under photochemical condition, this carbonyl will excite, leading to formation of CO radical and carbon radical, as you can see here. So this is radicals. This is the radicals. So this radical can react with this alkene, leading to formation of two regioisomers. Okay, like the C6H5, CO dot C6H5. So it can react either in this fashion, leading to formation of this radical, or it can recombine in this fashion, leading to formation of okay. So out of this will be more stable, as this radical is tertiary radical. Here the radical is primary radical, so this will be less stable, this will be more stable. Then it will undergo a spin inversion and recombination, resulting in the formation of oxytane skeleton. So this will be the major product that is formed, and this will be the minor product that will be resulting. So this is an example of Paterno-Bucchi reaction. So is it clear why the regiochemistry is favored for the major product? Because upon recombination of this oxygen radical with the alkene, the radical that will be formed will be more stable in the case of the major product, because the radical that is formed is a tertiary radical. But in the case of the minor product, the radical that will be formed will be less stable, that is a primary radical. Because of that, the minor product will be formed in less amount, and the major product will be formed in more amount, because it is favored because of the stability of the tertiary radical compared to that of the primary radical. Is it clear? If this is clear, now we can move to question number 15. Provide a mechanistic rationalization for the following reaction. So this is the starting material, and under H nu condition, it is resulting in the formation of this product. So which type of reaction is taking place here? So I will give a hint here. A Norrish type 2 reaction is taking place. So what is happening in Norrish type 2 reaction? Under photochemical condition, this carbonyl will excite, leading to formation of O radical and carbon radical, and then a gamma hydrogen abstraction will be taking place, leading to formation of a radical here. because alpha, beta, gamma. So this hydrogen will be abstracted, leading to formation of a radical here and OH, and here the radical will be present. Okay, then these two radicals will recombine, leading to formation of a cyclobutane ring. 1, 2, 3, 4. So that is this cyclobutane ring. Clear? So this is the mechanism under this compound gives Norrish type 2 reaction in which intramolecular hydrogen abstraction by the carbonyl oxygen from gamma carbon take place. Alpha, beta, gamma. So first under H nu condition, the carbonyl will excite, leading to formation of this O radical and carbon radical. Now a gamma hydrogen abstraction will be taking place, leading to formation of the radical here. Now this carbon radical and this carbon radical will recombine or cyclize, resulting in the formation of the final product. Is the mechanism clear? So this is an example of Norrish type 2 reaction. Okay. Now coming to next question. So this was a question from week 7 assignment. So we are having this ONO compound under photochemical condition. This will undergo uh, some reaction, leading to formation of the final product. So what is the final product? So this is not exactly a Barton reaction, but it is similar to Barton reaction. So what is taking place? So in Barton reaction, we have seen under photochemical condition, this ONO bond will cleave, leading to formation of O radical and NO radical, right? And then a gamma or delta hydrogen abstraction will be taking place, leading to remote functionalization. So in this case, that remote functionalization is not taking place. So first what is happening? ONO. Under photochemical condition, this will homolytically cleave, leading to formation of O radical and NO radical. Now, this upon formation of carbonyl, this bond will be homolytically cleaving. So, if we will number 1, 2, 3, 4, 5, 6, 7. Okay, this 1, 6 bond will be breaking, leading to formation of Me and an aldehyde here. Now, this radical will recombine with the NO radical, leading to formation of Me, NO, Me, Me, aldehyde. So, if we number, it will be like 6, 5, 4, 3, 2, 1, 7, and this can be, one second, this structure, it is similar to, this is a 1, 2, 3, 4, 5, 5-member ring now. Okay, Now this is carbon 6, MENO, carbon 7, ME. Now carbon 3, to that is connected carbon 2 and carbon 1. Okay, so this is 6, 7, 3, 4, 5, 2, 1. So this will be the final product. Hope you have made it correct in the assignment. Okay. So first this ONO radical will cleave, leading to formation of O radical and NO radical. Okay. Then this bond will be breaking homolytically, leading to formation of the radical here. Then this NO radical will recombine with this radical, leading to formation of this final product. Hope the mechanism is clear. Now moving to next question, that is question number 17. Provide mechanistic rationalization for each of the following reaction. So this is our starting material where the substitution is at para positions. Now under photochemical condition there is a scrambling of the substitution to meta position and ortho position. So how we are getting this A product and this B product? So that is the question. Okay, so here it will be undergoing an electrocyclization followed by then opening to give these two products. So it will be going through a prismane sort of intermediate. Okay, so let us see how the reaction is taking place. So for the formation of the meta product, as you can see here, 1 2 3 4 5 6. So here the electrocyclization is taking place between these two. See, 1, 2, 3 and 6. Here the electrocyclization is taking place. 4 pi electrocyclization is taking place, leading to formation of this intermediate, which upon a 2 plus 2 cycloaddition between these two, okay, will lead to formation of this prismane intermediate. Clear? First a 4 pi electrocyclization is taking place, leading to formation of this, okay, electrocyclization is taking place between 3 to 1 6 carbons, leading to formation of this intermediate. Then a 2 plus 2 cycloaddition will be taking place in this fashion, leading to formation of this prismate. Now this 3 4 bond will be breaking and a 3 6 double bond will form, and this 5 6 bond will be breaking and a 4 5 double bond will be formed, which is similar to this open book structure, okay, like this. Now this 1 2 bond is breaking, 2 3 double bond will be forming, and this double bond will shift here, leading to formation of 1 6 double bond. So you can see now this is present, like now this R group is coming to the meta position, as we can number 4, 2, 3, 6, 4, 2, 3, 6, 5, 1. Okay, so this is how the para substitution is getting converted into meta substitution. So here the first step is crucial, that is electrocyclization. So the electrocyclization is taking place between these two carbons. Then it will be going through this intermediate, which will lead to form a 2 plus 2 cycloaddition, leading to formation of this prismane. And once the prismane will open, it will give an open book structure like this, and this 1,2 bond will be breaking, leading to formation of the benzene again. So now the substitution have shifted to meta position. Okay, and how the ortho substitution is taking place? In this case, if we are numbering 1, 2, 3, 4, 5, 6. So here electrocyclization is taking place in this fashion between 1, 4, 5, 6. Electrocyclization is taking place, followed by a 2 plus 2 cycloaddition, giving this prismane sort of intermediate. Now the bond will be breaking in this fashion. It will lead to formation of an open book structure like this, and this bond upon breaking, it will lead to formation of the benzene again. And now the R group have redistributed to the ortho position. So this is how isomerization of or scrambling of substitutions of the disubstituted benzene is taking place. Is the mechanism clear? So first an electrocyclization, photochemical 4 pi electrocyclization reaction, then 2 plus 2 cycloaddition, followed by some rearrangements. Opening, prismane will get converted into an open book structure, that upon a bond breaking, it will lead to formation of the or electrocyclic ring opening reaction will be taking place, leading to formation of the A. So here a ring closing reaction is taking place, here a ring opening reaction is taking place. Similarly, here a 2 plus 2 cyclo addition, here a 2 plus 2 cyclo reversion. Okay, I hope the mechanism is clear. If there are no further doubts, we can move to last question of today's session. So that is question number 18. Give the product of the following reaction. So this is our starting material. Under photochemical condition, what will be the final product that is formed in this reaction? Dienone sort of system is this. Okay. So what is happening under photochemical condition? This carbonyl radical will get excited, leading to formation of this oxygen radical and this radical. Now this double bond will shift to this position like this. Enol radical will be forming and a new radical will be formed here. Okay, so this is a secondary radical. Now the CH3 group will shift to this position. A 1-2 shift of the CH3 group will take place, because the final once the shift will take place, we will be getting a stable radical. As you can see here, this is a tertiary radical. Also it is stabilized by this electron withdrawing ester group. Now proton abstraction and rearomatization, it will lead to formation of the final product. So this is the final product that is formed in this reaction. A1 the key step is this 1-2 shift of the methyl group. Okay, first this under photochemical condition, this ketone will excite, leading to formation of this oxygen radical and this carbon radical. Now this double bond will shift, leading to formation of this enol radical. Now this is a secondary radical. Then a 1-3 shift of the methyl group will take place from this position to this position of the benzene, leading to formation of a tertiary radical which is stabilized by this ester functionality. Now a proton abstraction and rearomatization. Proton abstraction and aromatization will take place, leading to formation of the final product. Okay, so this is the chemistry of the dienone radicals. So this is all for today. So this was the last tutorial for pericyclic reactions and organic photochemistry. This was the week 8 tutorials. So tomorrow we will be having a summary tutorials where we will be discussing problems based on pericyclic reactions, starting from electrocyclic reactions, then cycloaddition reactions, sigmatropic reactions, ene reactions, kilotropic reactions, followed by some questions from photochemistry as well. So hope to see you all tomorrow. Thank you.